Hi class, in this prac we're going to put together a two-dimensional DEM solver. This basically carries on from our lecture. We'll be writing the code to, in this prac, a very simple elastic circular particle DEM code. They'll be perfectly smooth, so we won't worry about friction, and in the next prac we'll actually include friction. So what I'm going to do in this first part, there's two screencasts for this prac. This first part I'll be talking about the code that I've actually put together as a basis for this DEM solver, and then in the next screencast we'll actually write the DEM solver. So on LearnJCU I've placed a zip file of the DEM 2D program. Now if you put that on your computer somewhere and extract it, then you'll have this folder, and we can actually open Visual Studio and have a look at what is there. Okay, so that opens up. Now you might be seeing this, or you might just see some empty screen like that. Now over here at the Solution Explorer we can actually see the files, the different program or different classes that I put together for this program. Now if you can't see Solution Explorer, like for instance if I do that, then if you click View, Other Windows, Solution Explorer, it'll come up. So the Solution Explorer just gives you access to all the different files in a program. So the first point of difference is that you note that what we've been writing up till now is we've been writing our code in the program class. You'll see that this actually looks a little bit different, and the reason that is that we're actually going to write a form program rather than a console application. A form program is like any sort of Windows program, so when you execute it'll open a window and there'll be buttons and things that you can press on that window. Now this is a little bit more advanced, and so as a result program actually has to open up that window, and then we have to handle what happens on that window. So there might be a button that says go, we need to handle the button rather than actually writing a program. So don't worry about that too much, I've done all of that for you. And I've done that in the form here. So if you double click on form 1, you'll see this come up, and what we've got is a single button that says execute and a picture box. So everything that's going on, if we have particles bouncing around against each other, that will be shown in this picture box, and the execute button is what we need to manage. So once someone clicks on execute, that will actually fire the program, and we need to handle how that behaves with DEM particles. Okay, and how that actually behaves is in this DEM engine class. So if you double click on that, what happens when anyone clicks on this execute button, it will actually fire this execute method here in the DEM engine. So everything else you don't need to worry about. In execute, this is the code that we're going to write. This is where we're going to write the DEM program to solve. And I've given you just a simple little example here that, without going into too much detail on the other things, I create a problem space, so x coordinates between 0 and 0.3, y coordinates between 0 and 0.3. I create a list of particles and a list of boundaries, which I'll discuss in a second, and I actually set one particle in the center of space, set a boundary, and then call this output a method. Now this output method is what actually draws a picture to that picture box in the form, so that's what actually writes something here. So if we have an integration loop in here, and every time we call this output it will render a different image to this screen, which is what we want. Now if you delete one of the brackets in output and write it again, it'll tell you exactly what it wants. So it's for writing to the problem space, it wants the bounds in max and min x, max and min y. It wants an array of particles, array of boundaries, and the time. Now the time is, if we have a time loop, we want to actually render what time each picture is related to, so you know real time what's happening on the screen. So I've just set X max and min, Y max and min, the particle list we defined, the boundary list we defined, and 0. And if you execute the program, you'll see what happens. Okay, so the form comes up like this just by default, and then if we click execute, you get this image. So we set the time as 0 seconds, so it's showing that it's currently 0 seconds. You have a particle out here in the middle of space, a boundary near the bottom of the space, and nothing happening because we haven't actually created any reasoning for this particle to be moving or doing anything. So if we put a time loop here and actually put a couple of particles and put rules about when particles bounce off each other and things, that will all be rendered here, but this is just a little example. Okay, so if I, for the moment, comment out this, so we could put 2 forward slashes to the left hand side of all of this code, or what we can use is the block comment, so a single forward slash and a star, and then a star and a single forward slash to close it out. So by putting that either side of a section of code, that actually comments out the whole block, so we don't need to write specifically 2 forward slashes to the left hand line. We can just comment out an entire block like that, and then we can put our code here, which is what we're going to do. But before we do that, I'm just going to explain a couple of these classes over here that we can actually use for this program. So I've put together a few classes that we can use for DEM code. They're pretty generic type classes. So one is going to be a 2-dimensional vector, one is a DEM particle, and one is a DEM boundary class. So vector is the easiest to understand for starters. So if you click on vector 2D, double click on it, that will open up this code that you see here. Okay, so in this code what we have is basically what is contained inside a vector. So vector will behave exactly like a double or integer that you've been using in the previous pracs, except that we know vectors are more complicated than just a single double precision number. In this case, if we've got a 2D vector, we'll have an x coordinate and a y coordinate, and we'll use double precision values for that. So these are just private variables, and these are the public accesses, so they're exactly the same. So when you look at the vector 2D class outside of this code, you can access the x and y coordinates. Alright, so let's look at that in the actual DEM engine code. Alright, so if we want to create a new vector, we do it in exactly the same way that we've done arrays and doubles and things in the past. So write vector 2D, let's call it myvec1 equals new vector 2D, and then if you put a bracket, you'll see what options we can actually do for input. So you see we're looking at 1 of 3, and the first one is you can just close the bracket out, and what that gives you is a completely empty vector, so 0 for x and 0 for y. Now if you use the down key on your keyboard, you'll see the second option. We can create a vector from an existing vector, so if we want to copy a vector, this is how we would do it. We would just input the existing vector here and it would copy it. Or if you press down again, you can see that you can tell it an x coordinate and a y coordinate, and this is what we're going to do. This is what you would probably use the most. So if we want a vector, let's say at 0.15 and 0.15 and close that out. Now we have a vector at that position. If we put a breakpoint here and execute the program, execute, obviously it skips over this. This is commented now. It's executed that and got to the end, and if we hover over myvec, you'll see that you get this text here, and it tells you x and y equals 0.15, 0.15. If you click the plus, it will tell you that x is 0.15 and y is 0.15, exactly what we want. Okay, so stop. Alright, Now, the benefit of using classes means that you can actually handle this as a single entity, so as a vector, or you can actually look at the components. So maybe if we wanted to know what the double precision x and y values were, we can do this. So if we want to know what the x value is, we can type myvec1 and use the decimal place, and then you get this drop down. So these are a bunch of methods that I'll talk about in a second, but at the bottom here we have x and y. So if you choose x and then double y val, okay, so now what we're saying is we're determining or extracting the x value from myvec and setting that to this double precision value, and we're extracting the y value from myvec and setting it to the y val. And if we run the program, stopped at this breakpoint, now we look at x val is 0.15, y val is 0.15. So we can actually access the components of a class, like the vector class we've made here, by the decimal place. We can work out what each part of that vector is. Now, like I said before, we've got some methods inside the vector class. So if I just type myvec dot, you can see what those methods are. We can calculate the cross product, the dot product, the magnitude of the vector. We can rotate the vector or write it to string. So the main ones we'll look at is cross product, dot product, magnitude, and rotate. So those are the things we're going to be using in the actual DEM code. So just as an example, let's take magnitude, and if we open brackets, you'll see the only option for magnitude is just to open and close the brackets. And if you hover over magnitude, it'll tell you on the left hand side of the top text there, double. So this is what it returns. So this will actually be a double. So if we say double mag equals, okay, and then run the program, we now hover over magnitude, and this is the magnitude of the vector if the vector is 0.15 by 0.15. You can calculate that by hand if you'd like to confirm. Alright, what we also might want to do is calculate the dot product. Okay, so if you open the brackets, you see that we have two options for dot product. The first one is just absolutely no input to the method, and it's a self dot product, so it's the dot product of myvec with itself. If we did a second dot product, myvec dot product, and press down on the keyboard, you see that the second option is to actually input what second vector it is. So you can take the dot product of one vector with another by specifying the vector in the input for the method. If we were to specify myvec1, you'd be taking the dot product of myvec with itself, so technically dot and dot 2 should be exactly the same. Let's have a look at that. Dot 2, 0.045, dot is 0.045 and dot 2 is 0.045. Exactly what we want. Okay, so you can also use cross product and rotate a vector as well, and I'll talk more about that when we get to specific examples. Alright, so let's just delete those parts of the code because we don't need it anymore. Alright, now what we might want to look at is the particle class. So if I double click on the particle class, you'll see how we have some private member variables here, exactly like we did in the vector class. So in the vector class we just had x and y. In particle class we got a few more things than that. Now you remember in class that I said that each particle will carry its position, velocity, force, radius, things like that. And we actually have variables inside the particle class for each of those. So each particle, exactly like a double precision, if exactly like a vector. If a vector has x and y values, each particle might have a radius, vector position, so position in the x and y, a vector velocity, so velocity in the x and y, force in the x and y, its own mass, and these last four are for that second equation, so the actual rotation equation, so rotation, angular velocity, torque, which is a force, and moment of inertia. Okay, so these last four we won't use too much, but the first five is pretty important to what we're doing in this prac. And what you might have already noticed here is that within a new class we can actually have instances of an existing class. So obviously you can have doubles, but you can also have the vector 2D class that we've created in this code. Alright, so if you go into DEM engine, we can actually look at how a particle class works. So if you type DEM particle and call it my particle, the way we create a particle, exactly like we did with the vector, is to go equals new DEM particle and then bracket, and again it has three possible inputs. One is empty, so every single value in the particle will be 0, so 0 radius, 0 position, 0 velocity, everything like that. If you press down on the keyboard, you see you can enter an existing particle to copy. If you hit down on the keyboard again, you can see that you put individual inputs. So the first one has to be a vector of position, a vector of velocity, a double precision mass, double precision radius, rotation, angular velocity, torque, moment of inertia, etc. Okay, so this is the one that we'll choose. Now if we create a vector somewhere else, like say here, then we can put that in this particle as the vector of position. Now what we can also do, instead of creating a vector here and then calling the vector, we can just put that new statement directly in line. So that's exactly the same as just actually creating a position vector. It's just creating it in the method rather than outside of. If we want to state velocity, velocity is 0, so we can just create a new vector with empty brackets. The mass of the particle might be, for the example that I had before, 0.00837 kilograms. Radius 0.00635, and then rotation, all these other values can just be 0. Okay, now we have a particle. What we might do is copy that and name them particle 1 and particle 2. Now we have two particles, and if we change the position of the second particle slightly to let's say 0.2 in the x. Okay, so now we can actually operate on components of these particles and look at things. So if I wanted to know what the position of that particle was, I can type my particle dot, and now you see you have all of these options down here. So if I scroll to position, and position is a vector, I can say okay, and actually assign that position vector to some vector. So I can pull out the position from a particle in exactly the same way as you pull out x and y coordinates from the vector themselves. Now we can go one step further because we know position is a vector. We can actually use the dot operand to the right of position, and you'll see now you have all of the vector options, and so we can scroll down to x. So I can work out what the x position of this particle is by pulling out the position and the x component of position. And so classes work in this way. Whenever you embed a class, you get all of the options on position, all of the options of the class that's encapsulated. So we could calculate, say, the dot product of the position vector in particle 1. We can do the same thing for particle 2. Okay, and if you look at the what's contained in particle, then we have all of those options that I talked about. So the angular velocity, the force, which is a vector, the mass, which is a double, the moment of inertia, position, radius, rotation, torque, and velocity. So we can use any of these terms based on a particle, and a particle carries all of its own values. So that's very useful to us when we're doing DEM stuff. The only other thing that we might be interested in is, we say bool, call it isContact. So bool is a Boolean operator, so either true or false. And there's a method in the particle class called checkContact. And if we choose that and tell it a different particle, so particle 2, what this actually does is check the contact between these two particles based on their position and their radius. So if they're overlapping, if they're in contact, this isContact will be true, and if they're far enough away from each other that they're not touching or overlapping, isContact will be false. And the way that you use that is perhaps if isContact so you can use that in an if statement, and if two particles are in contact with each other, you can calculate what the force between them is and then apply that. And the way that you would apply that is perhaps my particle 1 dot force equals new vector 2d, and alright, and rather than have zeros here, you would put what the force actually is, and that would assign the force between, say, two particles back to my particle. Okay, so this will become a little bit clearer when we actually start using these classes in the practical. The only other point worth mentioning is the DEM boundary class. If you double click on that, you'll see that a boundary has 2 points and a normal. Now these are vectors. This is a vector point of the left hand end of a straight boundary, and this is the vector point at the right hand end of a straight boundary, and this is a normal to the boundary, so a normal vector, unit vector. So if you define point 1 on the left and point 2 on the right, the boundary will be a line between the two, and the normal will be straight up. If you define point 1 on the right and point 2 on the left, it'll be a line between the two, and the normal will be down. So the normal just defines the outward direction of the surface of the boundary, sorry. So that helps us when a particle impacts it, the normal will tell the particle to bounce off in the outward direction. Okay, and you can just reference point 1 and point 2 and the normal if need be, based on the boundary, in the same way that you get the position of a particle or the x and y coordinates of a vector. Okay, so if we close those classes down and look at this DEM engine again. Okay, so what we're actually doing is creating a list of this particle class, the same way that or an array more so, an array of this particle class, the same way that we've created arrays of doubles in previous lectures, previous pracs. We're creating a list of boundaries, and when we actually set this particle, we set it to a new particle, we tell it that it is in the center of space, so 0.15, 0.15. We set the velocity as initially being 0, we tell it a mass, a radius, and all these other variables don't really matter because we're not dealing with them yet. We create a boundary, and we tell the boundary what the left hand point is and what the right hand point is, and then we come to draw it. You've got a particle list and a boundary list, and when you run the program, you see that our particle is in the center of space at 0.15, 0.15. The boundary is in the bottom section of space. So these are the two major classes that we're using, and vector is a major class inside of those. So I've created them for you so that we can actually write this code quite quickly. Okay, so that basically summarizes the parts of the DEM 2D program that I put together. The major conclusion from this is that you will write your program in this execute method inside DEM engine, and we'll be using the DEM particle, DEM boundary, and vector 2D classes. So if we delete that section, we will write our code in this execute file. Okay, so in the next screencast I'll actually write the DEM code.